Hi everyone, this is a continuation of the lesson on implicit differentiation. We're going to look at applications of implicit differentiation for slopes and equations of tangent lines. So in this example, and I've pre-put in what the function is, x squared plus y squared is equal to 20. It is a circle of radius square root 20, since an equation of a circle is x squared plus y squared is equal to r squared. Not that you need to know that yet. In part A, we're asked for dy by dx. Keep in mind that this just means y prime. So for part A, I'm going to write down the function again, x squared plus y squared is equal to 20, and then we'll take the derivative of both sides. Derivative of x squared is 2x, derivative of y squared is 2y prime, derivative of 20 is 0 since 20 is a constant. We need to isolate for y prime. So 2y prime is equal to negative 2x, subtracting 2x from both sides, and then divide both sides by 2y. We get negative 2x divided by 2y, and we've done this already, but it's worth doing again, minus x over y. So that's part A. Now we'll move on to part B. Slope of a tangent line. Notice that unlike questions where you ask for the slope of a tangent line for an explicitly defined function, in which case you can just be given an x-coordinate, for implicitly defined functions you often have to be given an x-coordinate and a y-coordinate. And the reason for that is that there may be two y-coordinates for one x-coordinate for an implicitly defined function. If you're asked to find the slope of a tangent line, the general process is m is y prime at the coordinate given, at the x, y coordinates that are provided. Now you will need to plug in both of these numbers because our derivative contains x and y. So let's do that. That's going to be m is minus 4 over 2, which is negative 2. So that's the slope of the tangent line at this point. And then part C, our tangent line is an equation of any line. Y minus y1 is equal to m times x minus x1. So with the information we have, y minus the y coordinate of the point that's given, so y minus 2, is equal to m, which is negative 2, times x minus 4. I'm going to graph that line in the same graph with the circle, just so you can see what's going on. Y minus 2 equals negative 2 times x minus 4. There we have it. So I'm going to zoom into that point at the coordinate, we're moving the wrong box. Move this box. I'm going to zoom into this coordinate. You don't want to know what's in front of me right now. Just lots of screens and gizmos and devices. Okay, I'm going to zoom in to the point 4, 2, zoom in, zoom in, zoom in. And you can't even see the difference between the red curve and the blue line. They are completely overlapping. That's what it means to have a tangent line at that point. It's like the blue line is just barely kissing the red curve, barely touching at that point. Okay, next example. This time we're asked for the slope of a tangent line in a more direct way. We're asked for y prime when x is 1 and y is negative 2. So to do this, we have to take the derivative. What are we at risk of missing? We're at risk of missing a product rule. Look at the second term, x times y. That's an A and a B. So when we take the derivative, we use implicit differentiation and the product rule in all locations where it's necessary. we get 3y squared y prime plus ab prime plus ba prime, which we've already done. We'll do it again. What's the derivative of 5y? It's not 5. It's 5y prime. If you want, you can think of this as the derivative of 5 times y to the power of 1. The 1 will come down, multiplied by the 5, and we'll have y to the power of 0 times y prime. Y to the power of 0 is 1, so we have 5 times 1 times y prime, which is just 5y prime. Derivative of x to the power of 3 is 3x squared, and then the derivative of 1 is 0. Okay, we have to plug in a, b, a prime and b prime. A is x, b prime, the derivative of y is y prime, plus b, the derivative b is y, and then a prime is 1. So 5y prime minus 3x squared. And then we have two options. Option 1 is to plug in x equals 1, y equals -2 right here. Option 2 is to isolate for y prime and then plug it in. I'm going to isolate for y prime because it's a good procedure to get practice with. So the 3y squared y prime, that's going to stay where it is because it contains y prime. The xy prime is going to stay where it is because it contains y prime. I'm going to subtract 5y prime from both sides to move it over. And then the -3x squared stays on the right. And the y times 1 gets subtracted from both sides to move it to the right. Because we only want pieces with y prime on the left, pieces without y prime on the right. Next step, I'm going to common factor out y prime. And I get 3y squared plus x minus 5 equals -3x squared minus y. I'm going to double check I didn't miss anything. Looks good. Right, now I'm going to divide both sides by that bracket. So 3y squared plus x minus 5. Now we're going to evaluate this. We're going to take those two numbers and plug them in. X equals 1 and y is equal to -2. Please check this calculation because I might make a mistake plugging numbers in. I might make a mistake everywhere, but especially plugging numbers in. So -3 times 1 squared minus y, so minus -2. And then divide by 3 times -2 squared plus 1 minus 5. Okay, so we'll keep simplifying. -3 plus 2 divided by 3 times 4, 12, plus 1 minus 5. So minus 1 on top. And on the bottom, we have 12 plus 1, 13. Minus 5, 8. So -1 divided by 8 appears to be the answer. Please check. Please confirm. Don't just copy my calculation. Like all calculations inside the notes and the videos, I invite you and I recommend that you redo them on your own. Not just to check my errors, and maybe I made a mistake, but more important is that's really how you learn, is doing stuff on your own. It's nice to be able to do these ones on your own because you can loop back to the videos and confirm, or loop back to the notes and confirm that you did them right. When should you do that? When should you redo the examples from the videos? I'd say as soon as you're done watching the video. So what I've seen some students do is they'll make 2 sets of notes. They'll make a set of notes where they're copying down what's happening in the videos. And then every time there's an example, they'll go to a different booklet or a set of paper, a loose paper off to the side somewhere, and they'll just write down the question. They'll say, okay, week 5 or section, what is this? This is whatever the section is, example. And then leave a space, and then example, leave a space. And when they're done, redo those examples on your own. Don't look at the notes unless you get stuck. If you get stuck, look at the notes, say, oh yeah, I forgot about that. Forgot about the product rule. Put it away, then go back and try it again. That process will help you with your homework. When you get to the homework, there should be very few questions that don't look like what we did. There will be some, and that's one of the reasons to ask for help in the various formats that are available. But for the most part, it'll be familiar. It'll be similar to what we're already doing. Okay, next question, we're asked to find the equation of a tangent line at 2, 3 for this expression. So an equation of a tangent line, we have some goals. Our goal is at the end, we want to have everything we need to plug in. Y minus y1 is equal to m times x minus x1. And actually, we have almost everything we need. We have y minus 3 equals m times x minus 2. We need to find m. We need to find the slope. M comes from, this is the slope. Slope m comes from y prime at 2, 3. So I'm going to write down the expression again. X squared plus y squared is equal to 3x plus 2y plus 1, and then take the derivative. Using implicit differentiation everywhere necessary, derivative of x squared 2x, derivative of y squared 2y, y prime, derivative of 3x is 3, derivative of 2y is not 2, it's 2y prime, and the derivative of 1 is 0. Again, I keep saying this, why is the derivative of 2y equal to 2y prime instead of 2? Because that's y to the power of 1. When we take the derivative of y to the power of 1, the 1 comes down and multiplies by the 2. We have y to 1 lower power, which is y to the power of 0, and then it's multiplied by y prime because this is implicit differentiation. We're taking the derivative of a function to a power. Even if that power is 1, it's still a function to a power. So we have 2 times y to the 0 times y prime. Y to the 0 is equal to 1. Anything to the 0 is 1. So we have 2 times 1 times y prime, which is 2y prime. Why did that not happen for x? And the answer is because x prime is always equal to 1. We don't need to write it. X is a variable. The variable with which we are taking the derivative with respect to. Okay, now I'm going to start isolating. I'm going to subtract 2x from both sides and subtract 2y prime from both sides. And then common factor y prime out. And then divide both sides by that bracket. And then as a final step, we're going to find m by replacing the x with 2 and the y with 3. So 3 times 4 divided by 6 minus 2, or 3 minus 4 divided by 6 minus 2, so we have minus 1 over 4. And please check all that. Because I may have made a mistake. And if I did, let me know and I'll fix it. I believe this is the last example. Oh no, there's 2 more. 1 more after. Okay. Now suppose we go back to the letter w that we were using in the chain rule. So w is our function of x instead of y, and we're asked for w prime at a particular xw coordinate. Well, in this case, we do the exact same thing we were doing before with y. We're going to take the derivative of both sides, d by dx. W is a function, so it needs a stealth chain rule. Needs implicit differentiation. So when we take the derivative, we get 2x plus 3w squared w prime equals 0 plus 5. We need to isolate for w prime, so I'm going to subtract 2x from both sides. And then divide both sides by 3w squared. So 5 minus 2x divided by 3w squared. And now we're going to evaluate it at x equals 3 and w is equal to 2. And when we do that, we'll get 3 comma 2, we're going to get 5 minus 2 times 3 divided by 3 times 2 to the power of 2. So 5 minus 6 divided by 12 minus 1 over 12. Also, please check this. Because I make mistakes plugging stuff in all the time. Last question. Suppose that y is a function of x and w is a function of x. Now we have two functions in one variable. And our expression has x, y, and w in it. And you're going to lose your mind. You're looking at this. I don't know how to do this. We didn't talk about that. Why is this an example? This isn't fair. Don't think like that. Think, what have I always done? Why would I change the way I've already done what I've been doing? What reason do I have? If I'm taking the derivative of y squared with respect to x, it's 2y prime. If I'm taking the derivative of w squared with respect to x, like I do the same thing I did here. I'm going to get 2w prime. Just do that. So I'm going to take the derivative of that expression. It's asking us for y prime, so we're going to isolate for that part when we're done. And then after we're done isolating, we'll plug in all the data that x is 4, y is 2, w is 3, and w prime is 2. It looks confusing, but follow the same things we've already been doing. X is a variable, so it's the derivative of x squared is 2x. Y is a function, so the derivative of y squared is 2y to the 1 times y prime. W is a function, so the derivative of w squared is 2w to the 1 times w prime. And then 3 is a constant, its derivative is 0. I'm going to rearrange. Minus 2y y prime. I'm going to add 2w prime to both sides. And subtract 2x from both sides. And now we're almost there for isolating for y prime. We just have to divide both sides by 2y. 2w prime minus 2x divided by negative 2y. Now we will evaluate. Evaluate at x equals 4, y equals 2, w equals 3, w prime is equal to 2. And we get 2 times 3 times 2 minus 2 times 4, all divided by negative 2 times 2. So 2 times 3 times 2, 12, minus 8, or negative 4. We get 4 over negative 4, which is negative 1. So what is this object that we just calculated? We calculated the rate of change of the function y with respect to x at a particular coordinate. And this is kind of getting us ready for the next thing we'll do, which is called related rates. It's a type of word problem involving derivatives that look a lot like this. So imagine this question, but before we get to that function, we have a paragraph, and we have to create the function. And it sounds bad, and in some ways it is, but it isn't that bad. See you next time.